Alright, hi everyone. We are back again for our last 2019 AP Calc BC FRQ. This is number 6. It's a BC only topic. If you haven't watched all of the videos for the AB and other BC FRQs, check out the Star Tutors YouTube page. Those are all up there. I've written out solutions and walked through explanations for each of those problems, so you should check those out, especially if you're studying for the AP exams this May. Alright, let's dive in. This is the final problem. Number 6 on the BC test is, I think, at least for the last several years, always a problem about series, specifically Taylor series or power series. So just be prepared for that. It's generally, I would say, the hardest problem on the test, especially some of the final parts. And so we will dive into that now and work through how to do problems like these. All right, so they say that a function f has derivatives of all orders for all real numbers x. So that just means you could take as many derivatives as you possibly want, and you can plug in any x value into any of them. A portion of the graph of f is shown above, along with the line tangent to the graph of f at x equals 0. Okay, so this portion must be the graph of f, or a portion of it, and this line must be the tangent line. It also says that selected derivatives of f at x equals 0 are given in this table. So this is saying that the second derivative at 0 is 3, the third derivative at 0 is this, the fourth derivative is this. All right, part A. Write the third degree Taylor polynomial for f at x equals 0. All right, again, a typical part A question for one of these problems. They usually ask you to write some Taylor polynomial. So knowing the definitions of the Taylor polynomials is very key, and I recommend that you always write out the definition on the problem that you're doing, so you don't make small mistakes when you're trying to find this polynomial. So remember that, maybe let's first say that the general definition for the Taylor series of a function f is usually defined, I'll use n since they're doing n, the sum from n equals 0 to infinity of the nth derivative, I'll say like a Taylor series at x centered at x equals a. So the nth derivative at a over n factorial times x minus a to the n, right? So this is the full Taylor series. And a Taylor polynomial is just the sum of the first few terms of this series. So in particular, in our case, we're looking for the third degree Taylor polynomial, which means we're going up to terms that have degree in x equal to 3, and we're adding all of them up to that point, not just that single term. You have to add them all up. So this degree 3 Taylor polynomial will be first, the first term will be when n equals 0 in this sum. If n is 0, then we're taking the 0th derivative of our function. Okay, so that's just f. In this case, we're doing it x equals 0, so a equals 0 for our situation. 0 factorial, remember, is defined to be 1. X minus 0 will just be x raised to the 0, which is just 1. So this first term is just f of 0. Our next term, similarly plugging in 1, you'll get that that's the first derivative at 0 over 1 times x to the 1. The next term will be the second derivative at 0 over 2 factorial, which is the same thing as 2, but I'll write it as 2 factorial, x squared. And the third term, the degree 3 term, is the third derivative at 0 over 3 factorial x cubed. Okay, and so this Taylor polynomial I know exactly what it is. It's this. And the things I need to fill in are these values of the function and its derivatives at 0. And so luckily they give me all the information I need to find those numbers. So f of 0, that's just the value of the function at 0, looks like it's 3 based on this graph. So 3. The derivative at 0, remember that's the slope of the tangent line. Luckily they give me the tangent line, so I can find the slope of it, right? From this point here, we go down 1, 2 over 1. So that looks to me like a slope of -2. So this is going to be -2x. Our second derivative at 0, they tell us in this table, is 3. So this is going to be 3 over 2x squared. And our third derivative at 0 is this -23 over 2. So this is going to be minus 23 over 2 all over 3 factorial, which is 6. So that becomes -23 over 12x to the third. And that is our answer for the degree 3 Taylor polynomial. So one of the things I think that's important to remember about Taylor polynomials is that they have a very formulaic expression, and if you can remember how to write these down, then you know that you just need to find these coefficients. You just need to find these values for the function's derivatives at the center point. All right, good. So there's our polynomial. For part B, it says, write the first 3 non-zero terms for the Maclaurin series for e to the x. All right, so maybe let's just do that before we even read the next part. Remember that the Maclaurin series just means that your center is 0. Same way, that's what we are finding for f here too. So we're centered at 0. It's good to remember that the Maclaurin series for e to the x is just given by the sum from n equals 0 to infinity of x to the n over n factorial. Or you could, write this out as 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on, right? And they just wanted the first 3 non-zero terms. Well, these are the first 3 that are not 0. So step 1 would be, that first answer is 1 plus x squared over 2 factorial, or just over 2. This is the, degree 2 Taylor polynomial for e to the x. Now they say to write the second degree Taylor polynomial for e to the x times f of x about x equals 0. And the key idea here is, how do we do that? Well, we know the degree 2 Taylor polynomial for e to the x. We know the degree 2 Taylor polynomial for f of x. To find the degree 2 Taylor polynomial for their product, we just multiply them, and we keep all of the terms up to degree 2. All right, so what I'm looking at is I'm trying to multiply 1 plus x squared over 2 times 3 minus 2x plus 3 halves x squared. Okay. And if I multiply these things out, one way to do this is to start with your first term here and distribute it through all of the 3 terms on the right, and then move to the second term, distribute it through to all the terms on the right, and continue like that. So our first one is this 1 times 3 plus 1 times -2x plus 1 times 3 halves x squared. Now for simplicity, for the next one when I'm multiplying x through, I'm going to write the terms on the next line below, and I'm going to write them under the x's of the same degree. So for x times 3, I get 3x. I'm going to write that here. Then for x times negative 2x, I get negative 2x squared. And for x times the next one, I'm going to get 3/2 x cubed. And then for our last guy, we've got plus a 3/2 x squared minus x cubed plus, 3/4 x to the 4th. Okay, but again, I'm only doing up to degree 2, so I don't care about anything higher than degree 2. And so my Taylor polynomial that I'm looking for is 3. Negative 2 plus 1. Negative 2 plus 3 is 1. So 3 plus x. And then I've got 3/2 plus 3/2 is 6/2. 6/2 is 3. 3 minus 2 is 1. So plus x squared. This is my degree 2 Taylor polynomial for e to the x times f of x. Okay. Part C says to let h be the function defined by this integral. Use the Taylor polynomial found in part A to find an approximation for h of 1. Okay, so first let's just note that h of 1, that means plug in 1 for x. Now, we don't actually know what this function f is, right? They didn't tell us, they just showed us part of the graph, but we don't have an equation for this. So that's why we need to use something to approximate this, and they're telling us to use the Taylor polynomial that we found in part A to do that. So we're going to say that this is approximately the integral from 0 to 1. They want us to use that t3 of x that we found. So going back up to our part A, we found that that was 3 minus 2x plus 3/2 x squared minus 23/12 x cubed. So I need to rewrite that out. Make sure I don't make any mistakes. You always want to double check your work when you're doing these problems, because one little computational thing can be frustrating. Although they do give partial credit, so if you do that, don't lose hope. Let's see, make sure we wrote that down right. Minus 3/2 plus 3/2 minus 23/12. Okay, I think that looks right. Alright, and now this is an integral that we can compute, right? So that's all they want us to do. We find the antiderivative, so we've got 3x minus x squared plus 1/2 x cubed minus, this is a 4, need to divide by 4. This is not a pretty number. 23 over 12 times 4 is 48 x to the 4th. We're evaluating this between 0 and 1. So we plug in 1, we get 3 minus 1 plus 1/2 minus 23 over 48. And then we'll subtract what we get when we plug in x equals 0, which is thankfully just 0. Okay, and then if we want to simplify this, I suppose we're going to need it in terms of 48s. So let's see. Well, first let's simplify some of the other numbers first. So 3 minus 1 is 2. And 2 plus 1/2 is 2 1/2, which is 5/2. And 5 halves, if I want to write that as 48ths, I need to multiply by 24 on the top and bottom. 5 times 24. Let's see. 24 times 5, 0, 2, 12, 10, 12. That sounds right. Okay, 120 minus 23 over 48. So 120 minus 23, that'll be 97 over 48. Okay, that is our approximation for h of 1. Okay, finally, part D, typically the hardest part, so don't panic if you don't know how to do it. It is known that the Maclaurin series for h converges to h of x for all real numbers x. It is also known that the individual terms of the series for h of 1 alternate in sign and decrease in absolute value to 0. Use the alternating series error bound to show that the approximation found in part C differs from h of 1 by at most 0.45. Okay, so this is a mouthful, right? The first few sentences, basically all they're telling you is that the series for h of 1 is an alternating series. Notice here the series alternated sign. They're saying it continues to do that if you do the entire series, every power of x. And since the terms decrease in absolute value to 0, by the alternating series test, this series is going to converge. And what does it converge to? It's going to converge to h of 1 based on this first sentence. All right, all of that to say that you can apply the alternating series error bound, and that's what they want us to do. So the alternating series error bound, what does that say? It tells us something about the difference between the actual value for h of 1 and our approximation, this 97 over 48. That difference is what we call our remainder or our error. And the alternating series error bounds tells us how big that error could be. So I'll let r sub 3 of 1 denote this is the remainder that we get. This is like the difference between h of 1, the actual value of the function of h at 1, and the approximation that we found, which was really like our, well, yeah, I'll just say the approximation we found, which was 97 over 48, right? And in absolute value, the alternating series error bound says that this is at most, so this bound says it's at most whatever the degree 5 term would be at x equals 1. So this is like the degree 5 term of the Taylor series, or the alternating series in this case, in absolute value at x equals 1. So this is an absolute value, since it's alternating. So it could have a negative sign if we want it to be positive, since this side's positive. All right, and so what we have to do is we have to figure out what this next term, this 5th degree term, would be if we were going to do that. And in order to find that, we have to know what the degree 4 term of our Taylor polynomial for f would be, so that we can integrate it. So let's recall, so this whole thing is going to be equal to the integral from 0 to 1 of our 4th degree term of our Taylor polynomial for f, which should be the fourth derivative for f at 0 over 4 factorial times x to the fourth. So going back up to the table at the top, notice it says that the fourth degree for f at 0 is 54. They didn't just tell us that for no reason. We hadn't used it yet. This is where we have to use it. So this guy, this number is 54. So this is the integral from 0 to 1 of 54 over 4 factorial is 24, x to the fourth. All right, we can simplify that a little bit to become, let's see, what does this become? Divide by 4, we get, well, divide by 2 at least. 12 and 27. And then we could divide by 3, 9 and 4. Okay, 9/4. Now we can actually compute this. So finding the antiderivative, we get, we raise this, we increase this by 1, so that's 5. We divide by that new exponent, so we get 9 over 20 x to the fifth from 0 to 1, which is 9 over 20 minus 0, so just 9/20. So in other words, this error is at most 9/20, and 9/20 is the same thing as, if we want to make that over 100, we multiply by 5, which is 45. This is 0.45, which is the bound we wanted. And that's how you use the alternating series error bound to show that your error, your difference between your actual function and your approximation, is at most some number. And it's in the alternating series case, it's at most the absolute value of the next term that you left out at your given point that you plugged in, which in our case was 1. All right, there you go. That is how to solve this number 6 FRQ on the BC test. Again, one of the hardest, for sure, I think the hardest problem on the test, but even though it's the hardest problem, it also has parts which are really tangible, like this one about the Taylor polynomial. If you just remember this definition and are able to think through how to find these numbers, you're going to get some points there. So just remembering that on the AP test, you're not expected to get 100%, right? A 5 is only 75%. Right, a 3 is only 50% of the problems. So remembering to manage your time, not get stuck on any one particular part or problem, and working to get partial credit, right? Especially on these FRQs in this last section when you have an hour and you have 4 problems, like doing the parts that you know how to do and getting those points, and then going back to some of the harder parts and thinking those through and spending more time there. But not letting yourself, just stare at a problem for a really long time when you could be doing other parts of other problems that are easier and getting those points there. So, best of luck to all of you as you're studying for the exam. Again, my name is Caitlin from Star Tutors, and I wish you all the best.
Don't forget to subscribe and hit that bell for all future notifications.